Welcome back. Well, previously we calculated how to determine the reactant concentration on each location R in a spherical particle. We ended up with this equation, and that involves the reactant concentration at the interface, the distance from the interface, the reaction constant, the diffusivity, and the particle size. Now that we can determine the reaction concentration on each location in the particle, we can also calculate the effective reaction rate and thus the effectivity factor. First, let's see how we can calculate the observed reaction rate. If we use the reactant concentration equation in the mass balance over the slice, and we integrate over the entire particle, so from position 0 to the position R, we get the overall observed reaction rate per particle. The hyperbolic cotangus in this equation stands for e to the power x plus e to the power minus x divided by e to the power x minus e to the power minus x. If no internal mass transfer limitation occurs, the reaction rate per particle would be minus K1 times the concentration at the interface of the particle times the total volume of that particle. And that gives the theoretical maximum possible reaction rate in that particle, by assuming thus that the concentration of the reactant in the particle is equal to the reaction concentration in the medium and the bulk. The observed rate per particle that we just found via working out the microbalance over the slice can be compared with the theoretical maximum possible reaction rate per particle. So by dividing the observed rate by the theoretical maximum rate, you will get the effectiveness factor eta E. By doing that, you will obtain this formula for the effectiveness factor for the first order reactions in spherical catalyst particle. It's quite a formula. But what we obtained is an equation for the effectiveness factor, and when you look at it, you will recognize that it only depends on the size of the particle, the big R, the reaction rate constant K1, and the effective diffusivity of the reactant A in the particles, the DAE. But I must admit it still looks quite complicated. And therefore we introduce the Thiele modulus. That's a dimensionless number that groups the radius of the particle, the big R, the diffusivity, and the reaction rate constant K1. The Thiele modulus for a first order reaction in a spherical particle is the volume of the particle divided by the outer surface of the particle times the square root of K1 divided by the diffusivity. So if we now combine the Thiele modulus with the equation for the effectiveness factor, the equation that we got looks at least less horrible. So if we plot the effectiveness factor as a function of the Thiele modulus, we find this graph. The effectiveness factor will go down with the value of the Thiele modulus. So that means that for small Thiele modulus, so for particles with a small radius r, or when the reaction rate constant is very low, or if the reaction diffuses easily into the particle, or a combination of those factors, the effectiveness factor will approach 1. And that means that mass transfer limitation in that case does not play a role. So you are now able to find the effectiveness factor for a first order reaction via this Thiele modulus. The only parameters that you need to know are the radius of your particles, the diffusivity of your reactant inside the particle, and the first order reaction constant K1. If you substitute the values for the effectiveness constant into your overall mass balance for the reactant A, you will be able to find the required volume of your reactor, or in case of a batch reactor, the required residence time for the reaction. Good luck.